Now, without further ado, it is my pleasure to introduce the speaker for tonight's lecture, Enzo Cosentino. Enzo is a senior expert at Airbus in composites and technical authority for wings, with extensive history in working in the aerospace and aviation sector. Enzo?
Thank you, Sam. Hi, everyone. My name is Enzo Cosentino. Before I start, I'd like to thank you, Sam, and the Royal Society, Aeronautical Society, for inviting me, and Rebecca for hosting me as well. Today's presentation I think it's a sustainability week, and my job title probably is not extremely explicit, but my field of expertise is composite structures, which can play a significant role in sustainability, but to a certain extent. Okay, so it was difficult to find the real focus on this presentation and link whatever we do in aerostructures to sustainability. The presentation tonight is also an attempt to provoke a bit. There will be some exaggerations, stories, which are not necessarily real. Some other numbers will be real, and I think you will be able to tell which one is real, which one is not during the presentation, I hope. And before starting, I prepared just a quick slide to introduce. Okay, so I'm Italian, graduated in 2001 and moved to work on with Leonardo. My first experience was helicopters, ATR 42, and then potentially the most interesting one, where I was in Seattle for 3 years during the development phase of the 787 fuselage and horizontal sailplane. And then I joined Airbus in 2006. And when I started my career, I was doing like nonlinear simulation, developing methods, analytical methods. And then I moved to something which is more what we call specific design. So I've been in charge of a team designing the wing of the A350-1000. And then I moved to what I do today, which is in the center of competence. So I am the technical authority for wings in Airbus, which basically means that I provide expertise, methods, certification requirements to the team in charge of designing our wings. So these teams are my customer initially. So I had them sizing and designing the wing. But towards the end of the program, I then become their customer because I need to collect all the documentation and then certify what we have designed. So I've been lucky enough to be able to work on potentially all the latest composite development, the 787, 350, Shacklet. I've been working on 400M and 380 for a bit. Today, my main focus is single aisle, so A320, Neo, XLR, 321, A220. And I was also nominated senior expert in composite analysis, which basically allows me also to stick my nose into R&D, strategy, and all that stuff. But go to the core of the presentation. I just wanted to start because sustainability is a bit complex as a topic. No one has got a 360 degrees view of cradle to grave life cycle analysis. It's very complicated, okay? So when we analyze numbers, I think we need to be careful and we need to don't believe the hype. So I prepared a slide in which basically I highlight the disadvantages of composite. What are the challenges which we are facing today? Cost is the first one. So if you look at that graph, at the right is the price of composites in commercial aviation. The first two are steel and aluminium. So as you know, aluminium has always been traditionally the baseline of our design. So you can clearly see that in terms of cost, there is a challenge. Okay, so they're definitely expensive. Emissions. So look at these numbers. In terms of energy associated to the extraction and processing of 1 kilogram of material, it's about 115 megajoule for aluminium. and more than double for the composites, okay? With the main difference that aluminium is nearly 100% recyclable, epoxy resins are not, okay? Thermosets, which is what we use in commercial aviation, are not recyclable. Sustainability. So I was shocked when I saw that data. So the aviation in general is responsible for a usage, global use of oil of 9%. It's big, it's a lot. And then the other challenge, look at the product value. These are data you can easily find on Wikipedia, okay? In that, I'm just comparing the fuel efficiency measured in terms of liter per 100 kilometers per passenger. And these are 3 aircraft, the 220neo, the A220, and the 737 MAX -8, okay? And this is measured over a short haul, so 1,000 nautical miles. So as you can see, the most performing is the 220neo, which is a metallic aircraft. And then the 220 and the 787 are comparable, but just bear in mind that the 787 again is metallic and the 220 is a composite aircraft. So it seems that the main reason why we had started in the past to use composite, which is lightweight, is it seems it's not really delivering value. So if you do a logic implication looking at these numbers, so we're using a very expensive material to generate emission and public outrage because it's not recyclable. There is an issue also with depletion of natural resources because oil is a resource which we are using in a non-recyclable manner to deliver no value at all. Okay, so were I the Prime Minister, I would ban the composite. Okay, but in reality, this is a very, very partial view because these numbers are just numbers. If we start deep diving into these fake news, which actually is not fake news, is a way of structuring a message which can be highly misleading, okay? In terms of the cost is probably one of the parameters that we cannot really affect in engineering. However, if we look at that emission and public perception number, so those numbers refer to 1 kilogram of material, not 1 kilogram of flying material, okay? When we account for all the wastage, okay, the waste when we machine aluminium and the waste associated to the use of composite, those numbers change radically. So if you look at generic real figures, this is what we are talking about for 1 kilogram of flying material, okay? So that basically telling you that the two numbers are comparable. There is still a recyclability difference, okay? But when you go in deep diving into the detail in that parameter that we typically refer to as buy-to-fly ratio, composite, typical waste associated to composite goes from 5 to 10% of the material you buy. Aluminium, for some machine parts, you can go up to 90% waste, okay? And I hadn't told you before. Sustainability, look in terms of CO2 emissions. So we go from 9% to 2 to 3%. So the commercial aviation is responsible for 2 to 3% of the global CO2 emission, which is still a measurable number, but it's definitely not that 10%. And in terms of product value, if we reanalyze and compare the product over a medium haul mission, you can see that in reality, I don't have data for the 220neo available in the open literature, okay? But if you compare those two, you can clearly see that there is a certain advantage, okay? Also, I have to say that that comparison was unfair because the 220neo and the 737 MAX are designed for short haul. Potentially the A220 was designed by Bombardier for a slightly different mission. So that comparison initially was completely invalid because it was not a like-for-like comparison. It was really unfair. So in reality, you will see during the presentation, composites are delivering some values. And there is also a way to extract more values compared to what we're doing today. The other thing I want to mention is that composites suffer from fatigue in a much less pronounced manner than metals, okay? We know from data, again, available in the open literature, that the amount of inspections and repairs and part replacement associated to the usage of composite fuselage and wings is reduced compared to metallic aircraft by a factor of 2, okay? So probably 30%, 40% is the ratio between the two. So it requires less maintenance, less time on ground for inspections, which basically means that the company will buy probably 1 or 2 aircraft less because they don't need to provision for more aircraft whilst the main fleet is on the ground. So all this is not taken into account in that analysis. So what is the value which we are extracting out of the composite today? So to the left, you can see a typical life cycle of a technology. It's typically divided into 4 phases, okay? The eruption, a phase which is called frenzy, is typically referred to as frenzy phase, where people start to believe that that specific technology is the panacea, okay? It can solve all the issues. And then experience with the use of that technology, and a phase in which it's called synergies, okay? In which we start finding synergies between disciplines, between components associated to that technology, followed by a maturity in which that technology becomes a cash cow. And you can clearly see that there is not much value left, and it's typically followed by the next technological surge. On the right, you can see the usage of composite in commercial aviation. This is, in general, basically the curve you see is more or less an average between Airbus and Boeing, which are the 2 key players. And for convenience, I just reported Airbus product associated to the usage of composite. So you can clearly see that there was an eruption phase in which a cautious usage of composite for safety reasons was introduced. Then there was an expansion phase, and then 350 and 787. In my opinion, what happened is that we haven't achieved a full maturity of the technology. But when there was this, say, race between Airbus and Boeing to deliver the 787 and the 350, we had to prioritize safety, engineering time, and manufacturing cost, okay, to produce something which was, of course, safe, okay, safety first. So what we knew at that time, I'm talking about the design rules, the famous 10% design rules. Composite needs typically to be symmetric, okay? So all those rules, which were implemented 20, 30 years ago, were an insurance of safety for our product. So we basically were sticking to those rules, and we stabilized the technology instead of finding the synergy because of that, okay? So, and I believe that even today, there is still a lot of value in the technology, which we can still exploit before even thinking of moving to the next technological surge. And I will try and quantify this value during the presentation. What are these synergies which we haven't achieved yet? So in my view, there are three different synergies. Cross-product, which is typically associated to cost. I'm talking about modularity, for example, okay? Cross-disciplines, which we'll deep dive into this specific one. And you will see it's typically associated to the aircraft performance and fuel burn. And then there are also material synergies, okay? So at micro level sometimes, which are associated to weight and recyclability. Just draw your attention on performance of fuel burn and recyclability. Both these synergies can have a significant impact on sustainability as well. Why are we not able to find synergies in an easy manner? I think it's in the nature of big organization, okay? We need disciplines, okay? we need to delegate. Even Western democracy, we delegate power to the government, to the parliament, to the judges, okay? When you reach a critical mass of people, you need to delegate competence and power of decision. So I tried to simulate it's just a fantasy example. It's a company which specializes in designing doors, okay? And the task is to design and assemble a composite door. It's an easy task, okay? It's just a door. You need a wall, a post, you need some screws, and a couple of hinges. The assembly, very easy. And the product structure, extremely easy. Okay, 6 identical screws, 2 identical hinges. So as a concept, it's extremely easy. But what happens when we ask a big company to design something like this? So the first thing, a big company, sorry, forgot to say, the assembly and the maintenance is very, very easy. So a big company immediately would split into 2 teams, okay? One which is in charge of designing the door, and the other one which will look after the wall, the screws, the posts, and the hinges, okay? So first barrier created, 2 completely different disciplines. Let's follow team 1. So what team 1 does to design a composite door, it goes through a very complicated process, okay, with calculating loads, sizing, usage of FEM, using non-linear FEM, optimization, and then finally, after a big and complex effort, we reach what we call CDR standard. So we are at the end of the development phase, ready to push the button and start manufacturing. And typically at that phase, something always happens, okay? Let's assume that we have recalculated with the new loads, and we find that there is a weight issue. So the door is overweight. And then with people, we start panicking, okay? We don't know how to save some weight and put the door in production in a very restricted time frame. So typically people start proposing ideas. Someone might propose like, this could be a weight saving idea, but it's completely incompatible with the aim of that design. Eventually, the quick fix we always find is, okay, let's remove 1 ply. Okay, straightforward, easy. Let's see what team does, what team 2 does. Well, team 2 is made of very highly competent engineers, okay? So the first thing they notice is that because the load distribution in the hinge is not symmetrical, is not homogeneous, they start optimizing the hinge because you don't need all that material. And that starts complicating the product structures, okay? Of course, optimized hinge require different grip length, okay? So you cannot buy just 1 grip length, but you need to diversify your order and come up with at least 6 different type of fasteners, okay, required to install that door. Even the post, okay, why do we need 1 material? Given that the top is reacting something in tension, the bottom is only in compression. So why don't we optimize that post and we use a good material in under tension for the top and then material which is good under compression for the bottom? Again, product structures gets more and more complicated. Then what happens is that during the assembly phase, because we have removed in a rush 1 ply, the door experiences distortions. So the 2 hinges don't fit flat to the wall, and we require some packers, top and bottom, as part of the assembly. And then this can happen during the in-service of that part, okay? Because we have optimized the hinge and we have generated the need for using several grip lengths, we have created something which is prone to human errors, okay, mistakes. So sometimes the assembler has used a incorrect grip length and the customer are experiencing loss of fastness, okay? So what is the morale of this story? That basically generating physical competence barriers, optimizing against non-optimal criteria, generate basically an assembly, a product which is complex in terms of procurement, complex in terms of assembly, and potentially requires a large stock. It's got complex maintenance, No value added because it still does the door job, okay? Open and shut. I don't see any value added by this process. And it's most likely not to be recyclable. So why am I insisting on physical and competence barrier? Because the multidisciplinarity is a big value, which you will see after these slides. And I just wanted to bring a couple of examples when that multidisciplinary thinking has helped Airbus proposing solutions which seem to be innovative. So top left, you will see that bird is an albatross, okay? The albatross is the bird with the largest wingspan in the world. It typically can fly without flapping its wing, just using thermal current, okay, for hundreds of miles. Of course, it must be tiring, okay? So the albatross has got a special mechanism by which the wings can lock into position by a series of ligaments, tendons, and the specific shape of that joint. So the albatross basically locks its wing and doesn't make any effort to fly. But there is also a safety mechanism into the albatross because when he approaches cliffs, he might see sudden gusts due to the change in the shape of the territory. Okay. So there is a safety mechanism by which when the wing see a gust, it unlocks easily, protecting the joint. And that concept has inspired what we developed a few years ago. It's called semi-elastic hinge, which we have a video. Basically follows exactly that example and was inspired by that idea. Okay, so what you'll see at the tip is a foldable tip, wing tip, which can release, okay, and unlock if the aircraft experiences a gust. So basically it doesn't transfer a big moment to the rest of the wing. It protects the wing, but the aircraft can still fly. That was a test with a model done by a mixed Airbus and potential University of Bristol team. So that idea was generated by someone who was interested in a completely different discipline, the albatross. Top right. So this is called Venus flytrap. Okay, it's a leaf, it's a plant, which has got a special leaf. This leaf has got sensors. So when a fly or an insect, a bug in general, touches these sensors, it activates a mechanism by which some cells inside the leaf start absorbing water, they dilate, and by doing so, forces the neutral plane on that to stretch. And when it stretches, it causes the buckling. It's a buckling of the lift. That has inspired myself and Airbus and another. So it was a joint, actually, task force between Airbus and Bristol to come up with that idea, which is a fully passive spoiler. So using that principle, you can see that, can you see that small device there? That device is a simple bistable composite, which is stretched by the wing itself when the wing sees a gust, okay? When it reaches a certain level of strength or stretching, so in plane compression, snaps through and acts as a spoiler. Basically, it disrupts the lift, alleviating the load, and then it goes naturally back to its original position when the gust is over. So why has that lift inspired this? Because basically, the characteristic of that lift is that the snap through happens suddenly, because if it doesn't, the fly would realize he's being captured and it would fly away. So you need something. It's a combination of orientation of cells, stiffness in our case, geometrical shape of that lift, which forces the lift to stay in its original position and suddenly snapping through, which is what we want for a device like that. We don't want that device to start flapping about during normal operation because it will interfere with the flight, okay? And one of the things that we did to achieve or to aim at achieving these behaviors, so we want something stable until it's deployed, was to try and mimic that behavior. Sorry. Okay, so where are these synergies and why a multidisciplinary approach, at least within my remit, okay, structures? To the right, you can see that three typical phases of the development of an aircraft, okay? Initially, it's the overall aircraft design, the concept phase in which we understand what the overall stiffness of the aircraft should be, the mission, the overall architecture, number of ribs, all these things, okay? So this is a very established process in all the aircraft makers worldwide since the 50s, I would say. Then once that phase is complete, it goes on to the specific design. We start sizing the covers, the spars, the ribs, everything, okay? And by doing so, we produce something which is extremely complicated, okay? Which typically we size, and we can only so we are typically structured to operate in such a way that what we can do best is design to minimum weight to an RF of 1.00, okay? But the series of requirements which we need to fulfill coming from the overall design phase is immense, and they're not necessarily using a similar model, a similar metric. Actually, typically the model where the requirement come from looks like that, okay? So that idealization, which is extremely sophisticated, okay, but it's the best they can do during that phase because they don't know, the structure doesn't exist. It's just a concept and an idea. But that simple model is defining a metric, okay, which we then need to fulfill by using a much more complicated model, okay, to simulate the real wing. And this is where the cross-discipline synergy hidden value is, in my view, because what happens is that that point there is our target. Let's say that the concept phase defines a certain target in terms of stiffness, load, weight to the design team, okay? Because we need to work to the assumption that that is the optimum we can achieve. Every time we operate on the structure and we try to save weight, for example, we deviate from the target. And because the target is the optimum, the assumption is that every time you, for example, you save weight, okay, you deviate from the target and you generate a loss in performance because the wing, for example, if you remove weight, your wing will be less stiff. And if it's less stiff, it's not really behaving as the concept phase has intentionally designed that wing to. So by deviating, you move towards a more drag, okay, environment in which you produce more fuel burn. And the typical optimization curve is represented there. So when we optimize and we design a wing, we try to move in the proximity of the target because we believe that if we move to the right, we will save weight, but we will penalize the customer, okay? And also the environment, because more fuel burn means more CO2 emissions. And all the effort of the last 15, 20 years in developing what we call multidisciplinary optimizers, okay, multidisciplinary optimization, can be summarized by that curve. Basically, a refined MDO, multidisciplinary optimizer, can give you the chance of moving further right with the same customer penalty, okay, with the same fuel burn penalty, basically. So you can still save a bit more material without additionally impacting your customer and the environment. In reality, if you could operate at design level in the same way an aircraft is designed, when we elaborate the concept, we would realize that in reality, every time you save, you remove weight, okay, the engine is carrying around less fuel, okay? So The real effect in terms of fuel burn is the summation of those two curves. So from one side, you have a wing which is not behaving as an optimal wing. On the other side, the engine is seeing less weight. So when you do that sum, a real curve, in some cases, looks like that. Okay? And those 2 points, which we believed were there, in reality, are on that curve. Okay? But that curve is also telling you that there is an optimum there, and is still to the right. So the metric is completely different, something we had excluded initially, moving to the right of that curve, because we were under the impression of penalizing the customer. In reality, this is generating customer value, environmental value, and business value, because you're saving weight, you're consuming less fuel, and you need to buy less material. Okay? Those curves don't exist at the moment, but this is what I would like within my business to work on, trying to understand how to change the metric, because the metric is very important. It will affect the way you operate and the decision you make. And this is an example, okay? What is the effect of using a different metric in terms of sustainability, okay? An aircraft is a beast by which 98% of the emissions are generating during operations, okay? CO2 emissions is fuel burn. Only 2% of the emission are associated to the make of the aircraft. So material, extractions, assembly, that only accounts for 2%. So it's quite clear that having a more efficient aircraft is the key to move towards a more sustainable product. Weight, saving, and performance are key drivers. Okay. So if each point of that curve is a different wing with a different level of optimization, and then you can clearly see that the curve of saved CO2 emissions, because you are moving towards right, peaks exactly where you have the optimum in terms of customer value, in terms of performance. Okay. So that is straightforward, telling you that sustainability and customer value, which is one of the key parameters for a business, go hand in hand. Okay. And then I just did a simple study. What happens if, instead of focusing on removing weight and operating in a design environment that maximizes the performance, we only focus on recyclability, for example? What happens if we introduce in our wings a material which is 100% recyclable with just a 1% penalty in strength? Okay. This is what might happen. A 1% penalty in strength in an aircraft world could translate into hundreds of kilograms of weight penalty. And for each 100 kilogram of weight penalty, okay, that basically translates straightforward into 1,500 tons or more CO2 emissions for an aircraft during a life of the aircraft. So it's big numbers, okay? So the meaning of that curve is, yes, recyclability is extremely important, but we need to understand how to operate a recyclable material in such a way that it doesn't generate an unintentional, unsustainable effect, okay? But what we can do more yet. So changing the metric can help you optimize an aircraft in a win-win-win fashion for yourself, the environment, and the customer. But still, there is some more value in composite. Still today, we call plus minus 60 in the fiber orientation, non-conventional layups, okay? Which should be modern layups, really. But we still have a reluctancy to move towards something which we haven't experienced, again, for safety reason, for cost reason, because we might need to do many more tests. But the experience gained so far suggests that the usage of non-conventional layups or aeroelastic tailoring, for example, can move the initial curve upwards, generating again more value for the environment and more value for ourselves, because we will need to buy less material. And then something else, once you saturate the technology by starting using non-conventional aeroelastic tailoring, what else is left? Well, to give you an example, I think it's quite known that high aspect ratio wing are extremely efficient, okay? High aspect ratio wings are also extremely flexible, but the flexibility itself is a natural load alleviation mechanism by which a more flexible wing tends to alleviate the impact of external loads, external gas, in a vicious circle. So long wing, very efficient, but also self-alleviating in terms of load, enabling additional weight saving. But to achieve the flexibility we need to operate on the right enablers, okay? If we use a novel technology to suppress, you see these three bars at the right, these are the first three most critical failure modes on a wing, okay? Without mentioning what they are. The most critical on the left, constraining the wing to a certain flexibility. If we got rid of that failure mode, we could allow more flexibility on the wing. But if we focus all our effort and research in new technology, let's give an example, toe steering, okay, curved fibers. So the usage of curved fibers is still in a development phase, but it's the main advantage of composites over metals. The lack of isotropy is the main advantage, because you can channel your stresses, your stiffness in the way you want, which is something that you cannot do with metals. Okay, so for example, where can we use toe steering to enable more weight saving and less fuel burn? Let's assume hypothetically that these three failure modes are open hole. For example, in a lower cover, you typically have manholes to access the tank. Okay. The manholes introduce stress concentration and can be a critical failure mode. In the meantime, talking about composites, damage tolerance could be a critical failure mode. Buckling is a well-known failure mode. But let's assume that the failure modes are in this order, where the most critical one is the open hole. That is exactly the failure mode I should target, for example, when assessing the value of introducing toe steering, so curved fibers in a technology. If I focused that effort in producing something which has got a better buckling behavior, I would see no value whatsoever in the wing, because the wing will still operate constrained by the open hole. So focusing the right technology on the right technology for the right usage is the secret, the magic potion, in my opinion. And if we are able to do that and suppress that failure mode, we will enable more flexibility, so better performance, less material needed, less fuel burn. So we will enable moving towards an even higher curve. And this is what I dream of. Saturate the current technology and focusing the effort towards something that generates more value for everyone, passengers, customers, business, and environment, which is quite critical today. It is actually becoming, in my view, something strictly related to our safety. And then what's left? Sustainability in the sense of recyclability. So what I've discussed so far and says processes, I didn't mention recyclable materials. Okay? So we can still extract a lot of value out of the technology without introducing necessarily recyclable materials, because as you can see, if you sacrifice in terms of strength and property, you end up being more emitting than before. So my hope is that we are able to generate, with a more multidisciplinary approach, the base for exploiting better new technology until saturation, expansion, And then in the meantime, start developing what is the next technological surge, which could be or should be, in my opinion, recyclable, so that we tick all the boxes and we head towards a more sustainable future in which the impact of our aircraft is much reduced. And there is also much more value added in your product. Just to conclude, I have found an example in which a completely different industry has boomed because of serendipity, but a cross-discipline approach was involved. So what you can see that curve represents the growth of air traffic since the 50s until today. It has grown by a factor of 400. So I did some searches, and the tennis racket sales follows a quite similar curve. Okay, they're very similar. So since the 50s, the number of tennis players has grown by a factor of 200. Let's see what happened to the technology itself and why it was instrumental in that growth. You can clearly see that there are two events in that trend that can be identified. Let's see what they are. So in the 50s, the rackets were made of wood. Then metal, like alloys, were introduced. And then there was a first disruption, which was the introduction of carbon. Okay? The frame was made of carbon. The number you see there, 20 kilograms, was at the time the maximum tension for your strings, because the technology at that time was such as if you deployed a higher tension, the string would become loose quite soon. Okay, so really not good for customers that they had to buy a new racket or restring the rackets every other week. Okay, so that was a technological limitation, and that was also preventing a bigger frame, because when you have a very big frame, you need to operate on a higher tension, otherwise the frame will vibrate more. What happened in the 80s? A company called Wilson had an idea. What if I find strings that can be tensioned to a higher value to enable my dream, which is big frames to make tennis accessible to everyone, basically, and expand the market? Because the bigger the frame, the higher the chance that you hit the ball, actually. Okay. And they worked together with a company called Babolat, a French company. They started producing some fibers, which, by the way, were also sustainable because they were made of, I think it was a cow's bowels. Yeah. So it was a sustainable technology, much better performing, which enabled the creation of big rackets and opened the market to everyone, basically. And that was really disruptive. If you see the first trend here, the market was growing and it was not really sensitive to the price of the racket, because you can clearly see that when carbon was introduced, the price was higher. It's more expensive than aluminum alloys. But then when that disruption was introduced, the price went sky high, but actually the reaction of the market was impressive. So many more people were available to spend more money to buy these kind of rackets, because they had access to a sport they hadn't access to before, maybe because they were not talented. So it really disrupted the sport to the point that the champions you can see today, the X number ones, potentially some of them without that introduction would have been completely unknown. So to give you an idea of how disruptive that was, I got two samples. So non-tennis player, you can clearly experience the difference between the rackets. Sorry for the people online. So this is an old-fashioned racket, metal design, 19 kilograms tension. And this is the Tesco Finest version, okay? The latest design. So I encourage you to try to taste the difference. And then the last spike, of course, was the first introduction of a connected racket. So it was a racket with a sensor, which was basically recording data on your speed, acceleration, how well you were hitting the ball. And that, again, generated a spike in the sales of the racket, which basically resembles exactly what we are doing today in many industry sectors. Disruption, introducing, focusing on reducing the cost, and then the next innovation, which was more in line with today's passion, is digitalization. Let's see how the market reacted to that. So in the 80s, that was the market share between Wilson, Dunlop, Lacoste, and other brands in terms of racket sales. In 1992, look at how Wilson overcame the competition by just introducing that, using a multidisciplinary approach. So getting two disciplines to work together in a synergic manner to find a right solution for both the strings and the frame. Right? So the question is, was exploitation of hidden potential more disrupting than reducing cost? And why am I posing that question? Because sometimes there is more value in exploiting a technology than focusing on reducing the cost. Okay. But I leave all those reflections with you. And I'd like to conclude with a statement which is very optimistic, full of hope. It always seems impossible until it's done, by Nelson Mandela. And I thank you for your attention. That's the end of the presentation. Thank you.
Okay, I will pivot to what one of the chat describes as a very final important question. Is Enzo ready for tomorrow's China Open semi-final that will see Alcaraz facing Sinner?
I am ready, but it's not the semi-final, it's the final.
Oh, it's good.
Thank you for the question.
In that case, I'll bring the lecture to the close. Thank you very much, Enzo, for
my pleasure.
Interesting lecture. Again, I'd like to thank the staff and volunteers from the University of West of England for hosting us today, along with the volunteers of the Bristol branch who supported in organising this event. And lastly, I'd like to thank all of you in person for attending.
Thank you.
And all of you online for joining us this evening. Thank you very much all, and I hope you have a safe journey home. Thank you.
Thank you all.